Okay, this is the book Prevent and Reverse Hypertension by me, Pete Rogers, and I'm going to be talking a little bit more about how plasma membrane works with these ion pumps. If you haven't seen my video yet called Plasma Membrane or Membrane Ion Pumps, that's the one to watch where I go into more detail to really explain the metaphors that'll help you to remember this long term. So here's a sodium-potassium ATPase pump, pumping more sodium out than potassium in. So there's a net positive charge, positive current going out. The gradient ends up being 10 to 1 of sodium higher outside than inside. And it's the opposite with potassium. And again, it's based on the extracellular space being like the ocean, salt water. So high sodium chloride outside, and then the water rinses over to limestone, the rock, and that puts calcium into the water, calcium carbonate. So you're going to have really high calcium outside the cell. When calcium comes into the cell's activated to do whatever it does. Like a neuron will release its neurotransmitter, glutamate. Okay, if it's a skeletal muscle, cardiac muscle, vascular smooth muscle, it'll contract, for example. Okay, that's how cells work. They generate an electrical battery and they use that to power work. And then when they want to turn themselves off, they have to rapidly pump the calcium out. Okay, again, these are the concentrations. You don't have to know the exact numbers, you just have to know the concept. Salt water, sodium chloride is high outside the cell. The extracellular space is the same as seawater, where God originated life. Inside the cell is high in potassium. You have to know that. Okay, and then calcium is incredibly high outside the cell, 10,000, 15,000 times higher than it is in the cytoplasm. You have to know that too, because that is all cell physiology comes from those basic principles. And once you've got that locked away, you'll have a walk in the park learning cell physiology. Okay, here we're now talking about something a little bit different. Now we're getting into the concept of blood sludge. And what happens is the red blood cells have a negative charge on their outer surface called a zeta potential. If you just type that into your computer browser, a zeta potential of RBC, you'll see the negative charge on the outer surface of a red blood cell. And that way, two red blood cells, both being positively charged, being negatively charged, they will repel each other, okay? And that zeta potential will prevent the red cells from sticking together, which is what you want, so they don't clot. When you have a high-fat meal, the chylomicrons will stick them together, the LDL cholesterol, triglycerides will stick them together. Okay, so anyways, it's not just sat fats. You know, they had shown a long time ago sat fat would do it back in the 1950s, but in the 1960s they became more interested in polyunsaturated fatty acids, omega-6 cooking oils. And their effect was to cause even more blood sludge, more sticking together with the red blood cells, more rouleau formation. Peter Quo was a cardiologist in Pennsylvania in the 1950s who did this work. Meyer Friedman and Ray Rosenman in the 1960s did very similar work. And Roy Swank was doing real similar work as well, showing you how high-fat meals stick red blood cells together, creating blood sludge or rouleau formation, it's also called. And when that blood's all stuck together, now you're pumping thick blood through a blood cell, and that's going to raise your blood pressure. Because the reason you have a blood pressure is to pump blood to the top of your brain, your cerebral cortex, against gravity. And if you're pumping normal blood, it's like water. You don't need much pressure to pump it. If you're pumping thick blood, it's like a milkshake. You need higher pressure. High-fat meals make the blood like a milkshake, thick blood. Okay, and then if you have sodium, that vasoconstricts the arteries, and the narrowed arteries then, you have to pump thick blood through narrow arteries. That drives the pressure up. The vast majority of cells in the blood are red blood cells. Over 99% are red blood cells, by far. They're the main thing. So anything that increases the number of red cells is going to thicken the blood. Cigarette smokers have a higher hematocrit, more red blood cells in their blood. Their blood's going to be thicker, blood pressure is going to go up. Okay, if you're taking EPO, like those Tour de France bicycle riders to raise their hematocrit, higher hematocrit, more red cells in the blood pressure is going to go up. So the higher the hematocrit, the higher the blood viscosity. Blood viscosity is just a word to mean the thickness of the blood. And here's showing a slide there was a scene about something like this in the movie Game Changer about vegan diets and athletic performance. Basically, when you take blood out of the body and you put it into a tube, spin it down with a centrifuge, you get the red blood cells at the bottom. That's the hematocrit. You get the buffy coat, which is the white blood cells in the middle, and you get the plasma, which normally the plasma is translucent. You can see through it. But when you eat a high-fat meal, all the fat makes the plasma radio opaque. So that's a characteristic thing of thick blood as well. Okay. Well, I'll wait for the next talk before I start getting into all the stuff about myeloperoxidase. So today we just kind of covered a little bit about membrane ion pumps and a little bit about blood sludge rouleau formation. I hope you found that helpful.